Good morning. I welcome you all in today's lecture of the course Modeling and Simulation of Dynamic Systems. Today we are going to see how can we draw the bond graph model of any mechanical system. So, to create a bond graph model of mechanical system, it is advisable to have a good schematic diagram of the mechanical system, or we can have the word bond graph of mechanical system. Word bond graph is basically a way of representing the various system subcomponents and how the power flows from one component to another component. So, if you are able to draw the word bond graph of the system, then also it helps us in creating the bond graph of the system. A good word bond graph is created when we deal with system which are there in the multi energy domain. Okay. Now, there are three methods which can be used to create bond graph for mechanical system. These methods are method of flow map, method of effort map and method of mixed map. In the first method, that is method of flow map, we basically track the flows, okay, and with the help of that tracking of the flows we are able to draw the bond graph. Likewise, in the method of effort map, we keep track of the efforts, okay, and with the help of that we are able to draw the bond graph. And in case of method of mixed map, we combine both the effort map and the flow map approaches to draw the bond graph of the system. We will see one by one. Let us have a look at the method of flow map. Okay. Now, in this method of flow map, the single port mechanical C or R element may be attached to a one junction where the relative velocity of the ends of these elements are available. So, for example, if I have say a spring and these are the two ends of the spring, then I can make a one junction where the relative velocity between this end and this end is available, and there I can attach a C element. Okay. Likewise, I can do with the R element. So, the single port mechanical C or R element may be attached to a one junction where the relative velocity of the ends of these elements are available. So, say if this is your x1 dot and this is say x2 dot, this is say x2 dot, then basically here this will be x1 dot minus x2 dot. Okay. So, this is how we can do that. Then the single port I element may be attached to one junction where absolute velocities of generalized inertias are available. So, as you know that Newton's law is applicable only with respect to the inertial frame. So, we attach the I element to only that port where the absolute velocity is available. So, let us look at the general methodology for creating a bond graph model using the flow map method. Okay. So, first of all what we do is that we create a one junction depicting the components of velocities of inertial point. Okay. So, first a one junction is created which depicts the velocity components of velocities of the inertial point, and next we create one junction depicting the motion of endpoints of C and R elements, rather this one junction basically one junction depicts the motion of endpoints of these C and R elements, and then we can find out the difference of those endpoint motions, and then we can attach the C and R element there. Now, relate and connect these one junctions by transformer element if a lever relation exists between them, and if a gyroscopic relation and the feedback is there, then we can use a gyrator element. Okay. So, this is how we can proceed for drawing of the bond graph model. Now, create the relative velocities, as I said, between the endpoints of C and R elements by using a zero junction. As you know that the zero junction is a constant effort junction, or at the zero junction we have the summation of the velocities. Okay. So, depending on the direction of power we can have the addition or subtraction of the velocities. So, that is how we create a relative velocity port with the help of the zero junction. So, zero junction may be used for adding or subtracting of the velocities. Then attach C and R element to one junction where relative velocities of their endpoints are created. So, this is how we can do it. So, we can follow this procedure to draw the bond graph model of the given mechanical system. Let us explain this concept with the help of say some examples. So, first I am going to take an example of say spring mass damper system with the base subjected to certain ground excitation. Okay. This may be just considered as a simple model of a car with the wheels subjected to certain excitation from the ground. Okay. So, this is my mechanical system, and this mechanical system, as I said, consists of a mass, a damper, a spring, and this mass is subjected to here say excitation Ft, and there is a ground velocity coming to this Vt. Okay. Now, here we identify the two coordinates here. You can see that here it represents the velocity of the mass here, and this the velocity excitation which is coming from the ground. So, this is the description of this example. Now, if I want to draw the bond graph model for this system, so what we do essentially is that we create the two one junction here, and these two one junction basically represents the velocities this xm dot and this velocity xv. So, these are the two one junctions created depicting the velocity at mass point and the ground excitation. So, this actually represents the velocity of mass point, and this represents the velocity of the ground excitation. Now, then what we do, we take the difference of these two velocities using the zero junction. So, here you can see that I establish a zero junction here, and I take the velocity difference here. How does this velocity difference comes? Basically, you can see that here this power is in and this power is out. So, here if I take say our law of conservation, then here this velocity basically is going to equal to this velocity plus this velocity, or this velocity will be this velocity minus this velocity. So, this is how I get this velocity. Okay. And then as I said, the velocity depicting at 1 mv basically is this velocity difference. Okay. And once we get this velocity difference, we can attach the spring and damper at this velocity port. So, let us see how it is done here. So, this was our mechanical system, and I have taken these two velocity differences here, and now at this one MV port I attach a C element and a R element. Okay. So, this way I do it. So, this is done. Now, you see that we had this absolute velocity port for this mass. So, I attach a mass here, okay, and at this port there is a force acting here. So, I attach a bond here representing the force with the help of a SE element, and again here you see that at this the velocity of this port is decided by basically the ground excitation which is coming here, and so I attach a SF is equal to say Vt, the velocity here. So, this way this figure represents the bond graph model of the this mechanical system. Okay. And of course, with our usual procedure we can causal this bond graph, okay, as per the causality assignment procedure which we have seen. Okay. So, I can quickly just tell you how can we causal it. So, this is my I, say this is my SE. Okay, I have a 0 junction here, then I have one MV port here, and then I have one V port, and here I have SF is Vt, okay, and I attach a C and R element here. So, this represents a spring, this represents damper, and this represents our mass, okay, and this is my Ft. Now, what I do is first of all we causal the sources. So, this is SE. So, this will always be giving effort, and this is SF. So, this will always be giving flow. Now, after causaling sources, let us causal the storage element. So, the I element takes effort, returns flow, and C elements takes flow and returns effort. So, this is how this is done. And now, let us see the rest of the causality. So, here this is my one junction. So, and this is I is giving flow here. So, here this has to return the effort. So, this we have drawn. So, this is effort here. So, it will be flow here. Now, let us come from here, this is flow here. So, this has to be effort. So, the flow and flow here, this 0 junction has to be determined by someone and only this bond can determine that. So, let us put the effort stroke here, and this is a returning flow and giving flow here, and so this is one junction. So, only one bond can give flow. So, this is going to be the causal like this. So, this way we can causal this bond graph. Okay, and once we have the causal bond graph, we can derive the system equations as we have discussed in our previous lecture. There could be alternate way of drawing the bond graph also, and here in this alternate way we can create relative velocity junction for individually C and R elements. So, here you see that I create a relative velocity junction for R element. This is my inertial port, and this is my say ground excitation, and I take a relative velocity here, and this velocity can be given to this R. Similarly, I create a relative velocity port for C here. So, this minus this will be going through this, and here I attach a C element, okay, and rest of the things I have already explained in my previous slide. Again we can further simplify this bond graph. Here as you see that whatever power is coming, the same is going. So, this one junction is redundant. So, I can remove this one junction and make it straight. Okay. So, this R element can be directly connected to this 0 junction. Likewise, this C element can be directly connected to this 0 junction. Okay. So, this is how we do it. Okay. Now, suppose our spring mass damper system, the bottom end of it is fixed. Okay. So, we can use the same bond graph in fact and reduce the same bond graph. So, if the bottom end is fixed, this Vt, the ground excitation which was coming, that is going to be equal to 0. So, here you can see that we can put Sf is equal to 0. Now, if I put Sf is equal to 0, here you see if this power is 0, so this power power in this bond is also going to be 0. So, altogether we can remove this portion here, and when I remove this portion, this is what I get. So, SCI 0 and 1, and here C and R. Okay. And again you see that in this 0 junction, whatever power is coming, the same is going. So, this is redundant, and so we can remove this. This is what is also known as the reduction of your bond graph. Okay. So, I remove this 0 and this is how it comes, and again if there are two adjacent same junctions, then you can merge those junctions. So, this one and this one can be merged together, and we have the one junction like this, and SCI and C and R. So, you can see that the bond graph has been reduced. The previous bond graph has been reduced to the bond graph of that of a simple spring mass damper system, where all the components have got the same velocity is 1, and here this is subjected to a certain force represented by the SC element. Let us take another example. Okay. Now, here in this example you can see that there is a mass the M1, and this mass end is attached with a spring and damper, say K1 of stiffness K1 and damping coefficient R1, and its other end is fixed. So, this portion is that is what of the simple spring mass damper system which we have seen. And if I look at this portion, okay, then we have a mass and we have a spring and damper. Alright. So, this is another example of what we have seen in the previous example. Now, the difference is that here instead of Vt, the velocity is being now decided by this mass. Okay. So, this system will be subjected to the difference of velocities. Okay. So, to draw the bond graph model, it is very simple. Here we create a one junction corresponding to this velocity port of M1, and I attach a I and C and R corresponding to this. So, I have I, C and R. So, this way this completes my this portion, this completes my this portion, and for here I have this M2 here. So, I attach a I here, and this spring and damper will be subjected to velocity difference between this and this, that is x2 and x1. So, I just find out the velocity difference. This is the x1 velocity and this is the x2 velocity. Okay. So, I found out the difference here, and here I attach this C and R. So, these C and R are attached, and at again this one junction I attach the SE element to represent the Ft. So, this way I can draw the bond graph model for this whole system. Okay. And we can causal it as I explained you in my previous slides. That way we can causal the bond graph. Let us take another example. Here we have a spring mass damper system, and there is another mass hung from a spring, and the ends of these are attached to a lever. Okay. And you know that the lever we can model using a transformer element. Okay. So, that is what we can do. Okay. So, here I can simply create a one junction corresponding to the velocity of this M1 here. Okay. And I attach a I, and I attach a C and R here, and the Ft is here. So, this way this portion tells gives me the bond graph model for this portion. Okay. And then suppose I get a velocity of this point. Now, you can see from here, okay, you can see from here that this spring and this mass will be subjected to the same force. Okay. So, if this spring and this mass are subjected to same force, then I can attach a 0 junction, okay, and here I can attach a spring and I can attach a mass, or we can rather say that this spring and mass, or this spring will be subjected to a velocity difference, that is velocity of this point minus the velocity of this mass, okay, and then from I can take the velocity difference of these 2 points and I can attach a spring over there, okay, and of course then I will be getting the velocity at this port basically, okay, and this velocity and this velocity are related by the transformer modulus minus B by A. Why minus here? Because the direction of motions of this end and this end are going to be opposite, okay. So, that is taken care by putting a minus sign here, alright. So, this way we can draw the bond graph model for this system. Although here I have just talked a little about how we can model from the effort perspective, which I will be talking in next method, but you can always, as I said, you can always do it from the velocity perspective. If you want, I can just explain how at the other end we can do with the velocity perspective. We can find out actually this velocity here at the end of the say lever B, okay, and I have the velocity of this I is equal to m2, and I can take the velocity difference basically here in a 0 junction like this, and whatever difference comes here I can attach a spring. Okay. So, this is my K2 basically, alright, and then I can reduce this bond graph. So, reduce means here say this can be just written as or drawn at like this 0 junction, and here whatever is there the same is there. So, C K2, and here whatever power comes same goes. So, we have I is equal to m2. So, this is what is being shown over here. So, as I said we can look at it from the either perspective, alright, fine. Now, let us take another example. Suppose I want to model this car, okay. So, how can we do that? So, first of all we draw a schematic of the car. Here, as you can say, here I am representing say by C the centroid of the car here. This car has got say mass m and the polar moment of inertia j, and here I am using the 2 coordinates, one theta for the angular motion and say one for the vertical motion, alright. There are say the front suspension is at point A and the back is at point B, or rear is at point B. Here the front say suspension has got stiffness Kf, damping Rf, likewise the rear has Kr and Rr, and they are subjected to ground excitation V1t and V2t, and say this A is at a distance A from the CG and B is at distance B from the CG, and mg is the weight of the vehicle. So, now I want to model for the vertical dynamics of this car. Let us see how can we do it using the velocity method of flow map. Here we can see that say this is my one junction corresponding to the rotation of the car. So, I attach a polar I element representing the polar moment of inertia here, and I have here one junction representing the vertical motion of the car. So, I attach a I element here representing the mass. Okay. Now, I can see that here the XA motion will be X motion at A will be this vertical motion minus this motion. So, XC dot minus A theta dot. Similarly, B will be this vertical motion, and because of theta the velocity at B is going to be up again. So, this is XC dot plus B theta dot. Now, using this equation I can draw the bond graph. So, we see here say this is XC dot here. So, I can subtract or add velocity at a 0 junction. So, XC dot minus A theta dot. So, I have theta dot, I use a transformer with modulus minus A. So, here I get minus A theta dot. So, here this is XC dot minus A theta dot will be here, and here I get the velocity of point A. Now, I have the ground excitation V1t, and in a 0 junction I can take the difference of these, I get a relative velocity, and I attach a C and R element here representing the KF and RF. Alright. Likewise, I can draw the bond graph model for the rear suspension system here. Here in this case this relationship is implemented, XB dot is XC dot plus B theta dot. So, this is XC dot and this is theta dot velocity. So, if I take transformer modulus at B, the velocity here will be B theta dot and plus XC dot whatever is here, okay, and this velocity minus V2t will be here, and I take a difference and attach a KR and RR element here. Here further we can see that this relationship, that is we are drawing this bond graph using velocity relationship, and we can see that this relationship can be easily derived using this relationship, that is force and torque relationship can be established over here, that Fc is equal to, this is Fa and Fb here. So, Fc is Fa plus Fb, likewise Tc here will be minus A times Fa and B times plus B times Fb. So, that is how this is done. Then we can use the method of effort map also to draw the bond graph model of this system. Now, in the effort map we track the efforts. So, when a generalized force applied to an inertial point is such that the positive value of the force accelerates the inertial point in a positive sense, then this is how the power directions are represented, that is Ft and here this is I, alright. But if reverse is the case, that is when a force is shown which when positive produces acceleration in the negative coordinate direction, then this is how it is shown. So, I is represented here and this direction is reversed. Now, for creation of bond graph model using effort map, what we do is that we create a 0 junction for source of effort, and these 0 junction may be treated as the distributor of efforts. Then we decide whether the tensile force in C is to be taken as positive or it is the compressive force which is to be taken as positive. In linear spring such a choice may be arbitrary, okay, and for R element decide what kind of relative velocity is to be taken as positive. Again in linear spring this choice may be arbitrary, and addition of forces may be done using a one junction which is a constant flow junction, or the effort summation junction, and linear forces may be converted to couples using the TF element, and similarly the angular velocities may be converted to the gyroscopic forces using the gyrator element, and then reduce the bond graph using the method which we have already discussed. Fine. So, I take up say the same example which we have seen in case of method of flow map. So, here I have the spring mass damper system which is subjected to excitation from the ground Vt. Now, here you see that in here if I separate out this mass, then Ft is acting in this direction. So, here the direction of the force is going to be the opposite one, and likewise here this direction of force is going to be such that this opposes this direction. Now, let us see the this one. Now, here as I said, this Ft is going to accelerate this mass. So, we have this SE and this M being put like this, all right, or here what we see that in zero junctions, in these two zero junctions we can attach R and C over here. Okay. So, this way as I said, for model for this portion is complete. Now, you see that if I draw model for this portion here, the power direction is going to be in this direction, which is opposite of this one here, and again the power direction here is going to be in this direction, which is opposite of here, because here and here these directions are going to be opposite, okay, and rest of the thing is same. We can do it other way also, that is force due to spring and damper are aided and then distributed. So, here comes the force of the spring and here comes the force of the damper. We can add them up in this one junction and then they can be distributed here and here. Okay. So, this way we can do it, and this bond graph can be further simplified here by eliminating this 0 C and 0 R junctions. Okay. So, this way we can do that. Next method is the method of mixed map, and I am not going to talk about it here because it is a combination of both flow map and the effort map. So, part of your bond graph can be drawn using method of flow map and the part of the bond graph can be drawn using the method of effort map. Next, the last example which I just wanted to take you, the bond graph modeling of a robot. Say it is again a very good mechanical system. So, let us take a very simple example, say there is a one leg arm, and here at the end of it there is a mass M attached to it, and here this end a spring of stiffness say KT is there, all right. So, what we do essentially, we fix a coordinate system x y and say this is the direction for G and length of this arm is say L. So, what we do essentially, first we find out the velocities. So, to find out the velocity, we write the displacement equation, say x is L cos theta and y is L sin theta. Then we differentiate these relations. So, x dot is minus L sin theta theta dot and y dot is L cos theta theta dot. Now, what we do is that, suppose this one theta dot is the port which represents here the velocity of one end of the spring, other end of the spring is fixed. So, I have the velocity of one end of the spring, I attach a C element here, and then say this is my x dot velocity of the mass and this is my y dot velocity of the mass. This x dot velocity is related here by minus L sin theta into theta dot. So, here is the theta dot. So, I use a transformer with modulus minus L sin theta. So, here I get this velocity for x dot, I attach a mass here, all right, at this port. Likewise, using L cos theta as the transformer moduli here, I can get the velocity of y dot port. I attach the mass here, and in the y direction the weight is acting. So, I attach a SE element with this weight as mg, okay, and I attach the sensors here to say sensors of velocities here to measure the x dot velocity, y dot velocity and the theta dot velocities, and then I can causal the bond graph. Here you can see that this I element is subjected to differential causality, and we can remove that differential causality using artificial compliances which we call as a pad in the bond graph language. So, thank you.